在一起。
在一起，我用不到就是。
可以马上帮你查。哇，这个压力呢？看拍一点。
正义就正义坐这边的。
正义没有来，他没来。圣杰在，他等下来就被按手机。
不用紧，我们也是。
现在我非常高一点。
这是去哪里拿呀？
小红书。
别人像叫小青这种，我喜欢，应该看到一定。必须用。
你要怎么？这样剪吗？
你比我还适合。我过后跟你讲故事。没有，因为每次去弄他们。
没有他了。小时候很久了，到了那里回去挖到回带了。再来，下面。
去约会啊？
去 double date。
去约会啊？我们那边有2对情侣。
他生病，然后 Jackie 回家吧。
Jackie 开始做 FIP 了。
那会死。你做呢？你开始做多久了？
真的还没有开始做咩？我是不行啊。
我是这个，然后你是这个，这个是这个。要坐这里吗？
冷气那边。
你直接坐，不要坐。
你站着啊！你挡掉那边的冷气啊！我谢谢。就看眼眶那些。
是看那个历史材料。
你就可以去卖。
没有了，这是呢，毕竟是拿给他们从拿是在深圳部分的 idea 没有，真正拿 investment 毕竟是还没有办法。
就看眼妆。哎，长得就看你了。
你这个记者他们交流。
是你扣，我会跟你在一起。
不然是你哎不。
哎，我是你扣，但是我不是。你想去长的，就说明今天算你跟你扣直接。而且算你扣什么时候找东西要跟老公。
没有啦，没有钱。确实是这样讲。哦，圣洁讲啊。哦，这样。we need to read it.
Your answer is still there. My answer is
我觉得你的也蛮多最开心的。
that's why you see zero. Your answer is
我有瑞恩吗？你也跟 toxic 我觉得。我谢谢瑞恩。
耶。
你跟我要讲。
我星只有给尼克吧。咦是的，你这个给嘉义啊？我一直忘记哪里。
难怪他那个声音可以这样大声。因为奇怪，这么刚才，因为在我昨天在我前面用电脑开歌，奇怪，这么没有耳机。
他这样又没有多好，然后我就忘记了。
没事，我们整间宿舍都是他的舞台。
regarding the test. Sorry about the delay because people mess up the answers. Okay, so I have to key in again the answers in order for it to mark. Okay, and then at the moment it's zero because there's no answer that's given because people deleted my answer. Your answer is still there. Don't have to worry. Just my answer is missing. Okay? I will do it maybe tonight. Key in and then I release again. Okay? Oh yes, those came on the replacement class. Maybe I've heard already, but those who did not come for the replacement class, I mentioned that there is another test, practical test. Okay, this practical test is not in the plan actually, but I want to make it because it will help you in your exam. But this practical test is also open book test. There's no time limit here, but there's a time limit, but not like 1 day or 1 hour. No. I give you maybe a couple of weeks for you to do it. Okay? So you can submit the answer when you have. So it's not so stringent. Please pay attention to the practical test. because it might help you in your exam. Okay?
So I mean final go right. Code.
Yes, there is a code writing.
For one whole question is for code writing.
More than one, but different parts. Different parts.
So the failure rate will be high.
Huh? That's why I asked you to do this practical test yourself. Don't look at your friend's answer. Try yourself. Because if you get it right, actually you can check whether your answer is right or wrong. Okay. Okay. Let's move on to new topics. Is introduction to parallel computing. In here we're going to talk about the reason why we want to do parallel computing. In fact, I've mentioned this many times. And the component to build this parallel computing system. Okay, and what kind of models that we have, parallel programming models that we have, and some of the design of the parallel programs that we need to take into consideration. If otherwise, if we don't take into consideration, it might not give us the correct answer. Okay? And also, it will not help in expediting the performance. It means your performance is still slow or even worse. So you have to make sure that the design, actually it's not just design, it's your plan. How do you plan it? Okay? Now the motivation for parallelism is to accelerate computing, of course. This is to speed up the process. The second reason for it is because we already reached the limit of the physical limit of our computer speed. That's why you can see the speed does not increase anymore. Let's say, for example, the first time when the computer was created, it was running in kilohertz. Okay? Kilohertz, not megahertz even. And after that, the first personal computer was built on the silicon, and that was the first time the computer was running in megahertz. Okay? The first Intel processor was running at 8 megahertz. Okay, the predecessor of our Intel processor is a 4004. It's a 4-bit system. It was running at 1 megahertz. Okay? So the first Intel processor, 8 megahertz. 8 megahertz is very slow. 20 years forward from the beginning, right now we are at gigahertz. Okay, we are running at close to 4 gigahertz. But we stuck at this 4 gigahertz for a very, very long time. It never increased anymore. Okay? For several reasons. First thing is the physical limit of the speed of the electricity, how fast that we can go. Okay? It is actually limited by the speed of light. That's one thing. But of course, when you scale down, you make the elements smaller and smaller. That's why you see the American and the Chinese. China, they are trying to actually make our semiconductors smaller and smaller in scale, right? That's why you did like 14 nanometer, 7 nanometer. Right now you're talking about 2 nanometer. In the future, they are talking about sub-nanometer. Okay, as you decrease the size, and the speed is can be increased. Okay. But of course, they will face other kind of problem as well. In fact, our computer nowadays actually can run at 9 gigahertz, close to 10 gigahertz. But we don't run at that speed because the amount of heat that is generated is too large. So you need to have a big heat sink. Maybe you need a special cooler in order to cool down. So what they did that test, actually they are running at minus 80 degrees Celsius. That means you have to use cryogenic fridge to freeze the computer down to minus 80 degrees. Then only you can run at close to 10 gigahertz. Okay, so our computer, the one that we have now, can run at that speed only if we can manage the heat dissipation. Okay, so somehow we will eventually meet this speed limit. So what can we do? In order to overcome this, the best thing is to not scale up, but scale horizontally, meaning that you add more cores to run in parallel. Okay? That means you can have 10 cores running 4 gigahertz each. So effectively, you can think of running 40 gigahertz, right? Instead of have one computer that is running at 40 gigahertz. Okay, in the past, the computer is very expensive, and there's only one computer, and the computer can fit in one room and run very slow. So we have to do in batch. So if I'm a programmer, I have to write my program on a paper, and that paper I have to punch a hole, and that hole will tell the computer 1 and 0. So basically, I'm programming in binary. Okay, programming in machine language and in binary. There's no assembler for you. Okay, if you make mistake, you have to go and punch again the new card. And this card will be given to a person who is sitting at the person who actually managed the computer. He's going to feed in the card one by one. Okay, feed in the card and then produce a result. And the result is not printed on the screen, it's printed on a printer. There's a printer to print out the result. So by the end of the processing, the person is going to take that paper and then send it to you, post to you. Okay? So imagine you programming it this way right now. It's going to be very slow, right? Because it's going to take maybe 1 or 2 days just to run one time. If you make mistake, you have to repeat all over again, and then you have to send in again, and then you have to wait because it's batch. Because a lot of people also still want to use it. If you are in the last in the queue, you have to wait until then. Okay, so programming in the past is batch manner, so it's very hard. When silicon computer came into being, things are much better. Even though you got one computer, it also can fit one room. In fact, if you go to D block, the top floor, now you see everybody has one computer already, right? But in the past, there's only one mainframe there, one computer, and then a dummy screen, and a keyboard, and a mouse. And all of them are connected to one computer, which is the mainframe. And it is using time sharing. The computer is time sharing. That means serve you for a while, and then serve the next person. So it serves everybody equal amount of time, but very short time. And it does this repetitively, a very quick sequence. And you get a feel of having to use the computer yourself instead of having to do the batch manner. Right now we are time sharing. Okay, so that is in 1980s we get this time sharing. The computer is also still expensive. Okay, and then came the desktop era, which is 1980 something. That was where Intel came up with the first generation of our computer, 8088 and 8086 in 1981, 1982, right? So that was like 25 years back, 23 years back. Oh no, 34 years back, right? So there's that desktop era where everybody has his own computer. So right now we can program more conveniently. We don't have to go to the lab to do it. We can do it at home. Okay. Time sharing era, you still have to go to the lab or you have to go to the company or to your office to do it. You cannot do it. Okay. Desktop era, you can bring it home. You can have your own one. And after that, you have laptop era where you can bring along your computer. Right now, I can see everybody also using laptop now, right? Okay, and then now, even better, we have network era. Okay, everything we put in the cloud, we can even run the program in the cloud. You don't have to run on your computer. That means the computer can be a lousy computer, but the processing is done in the cloud, right? So that's the network era nowadays is here. So this is what I mentioned just now. I'm going to skip it. Okay. The computer architecture actually, when they come out with, they want to classify. Okay, classify. That's the name of taxonomy. So this flint is a computer scientists. In early stage of the computer architecture, they try to find how are we going to design our computer. Okay, of course nowadays we know that the first computer is single instruction, single data. Okay, I will mention to you later on. But Flynn actually comes up with different kind of architecture. It says we can actually create more types, more categories, not only one. Okay, our computer is single instruction, single data. And what it is, I'll mention in short one. Okay, I mentioned to you the instruction. I also mentioned to you the data. So it said when we do processing, we have instruction to process. And what do you process? You process the data. So these are the two elements, small elements, the important elements that you need in order to make things useful. Okay, of course, computer is a hardware that is going to do the processing, but you need instruction, you need the data, right? And he came up with this taxonomy, and ours in the past actually fall into the one on the top left. On the top left, which is the instruction is single, the data is also single. Single instruction, single data stream. This is our most commonly used computer at the beginning. Okay, the first era, we use single instruction, single data. Okay, so the processor is of this kind. When they design the processor, everybody follow this kind of architecture. Nobody else follow the rest. But nowadays, we feel that things are getting more powerful, and also we reach some limitation. We have to explore other kind of architecture. So they come up with different architecture, right? So how about GPU? GPU just existed, I think, maybe 15 years back. 15 years back, after our personal computer. Which architecture that you think GPU is using? Okay, GPU is actually using single instruction, multiple data. The bottom here, this one. Okay, this is our initial architecture that we use. Okay, and then GPU came out with time. We have single instruction, multiple data. Okay, that means you have one instruction. Every processor is executing that same instruction, but using different data to process it. Okay, so this program is the same program, but it's processing different data. Here, one single data, one single program. Right? And of course, if you try to map up, you can have multiple instruction, means two instruction or more instruction. And of course, this instruction must be run by the processor. So if you have two instruction, it must be run on two cores. Okay? And then you have only single data. That means two different programs are working on the same data. Okay, it can be something like this as well. Let's say, for example, you get the data from, let's say, from the environment. Okay, let's say the temperature or humidity. All right, but in the first one, you want to find out whether there is any pattern in the temperature and humidity for a certain reason. Okay, so you run that program for that. But you can use the same data to process it for other reasons. Okay, so that is multiple instruction, single data. Okay, this one I already mentioned. Then you have another one which is multiple instruction, multiple data. So multiple instruction, that means you got every core run the instruction, the respective instruction, multiple instructions. But they themselves also get different kind of data. Okay? They don't share the same data. Right? Currently, the most popular one is these two. Single instruction, single data, which is normally our computer using. But our computer itself also move into this four as well. For example, we have multiple cores right now, not only single core. Okay, we can do, our computer is more general. We can do this. Now we can do this as well because it's a multiple core and we can work on single data. And we can use our multiple core to work on different data but then single program. Or we can do something like this as well. So our general computer, general purpose computer can do all of them right now. Okay? But in the past when Flynn came up with this idea, that was like a very long time, I think maybe 1960s or 1970s. There's no such architecture, only this architecture exists during his time. But he has already passed away. Now we have this in our computer. Okay? And GPU is using this architecture. GPU is not so flexible, so it's only using one architecture, which is single instruction, multiple data. So this is how it looks like. The one program here. This is a pool of instruction, which is this, and then data pool, which the data comes in, used by a single processor. So these are all the old computers that we used in the past with this kind of architecture, including our desktop computer in the past. What you see here are supercomputer. For example, K1, this is a supercomputer of the past. During that time, it was running at megahertz, I believe. Can't remember what kind of speed it was. But right now, of course, our computer supersedes this, even this supercomputer. Okay, this one is how it looks like for single instruction, multiple data. So you can see that the processor P1, P2, P3 all running the same program, but the data that is fed to it is different data, right? So this is the process that is done by P1, P2, P3. This data comes from different data segments. Okay. And this one is multiple instruction but working on the same data. So you look at the instruction, they are all different for different purpose, but they use the same data in order to process it. Okay, and of course for a certain reason. And this one is used in space shuttle. Yeah. Space shuttle flight control. When they want to maneuver, they use different sensors to retrieve the condition and also to steer the rocket upward towards the destination. So they use all this data, but then the data can actually give them different kind of result, but you have to run with different program in order to produce that result. So multiple program running on multiple processors, but the data is the same data. Okay, the data here, it can be sensor data. For example, you collect the data of the temperature of the engine, okay, and also the speed of your acceleration and all that. So it comes from the sensor. It doesn't mean that the data is collected beforehand. It can be collected live. Okay, the last one is multiple instruction, multiple data. You got different programs, yeah, and the data also different. And this one is used in the cloud, especially. If you go to Amazon, go to Google, basically Google is doing this. The server farm is actually running multiple instruction, multiple data. And these are supercomputer of today's. So what we mean by serial and parallel. So serial is basically running everything in sequence. Okay, so you have these instructions. This is individual instructions. So the processor is going to run one by one. So it will not run this before it runs this. Okay? It will not run this before it runs this. So whatever that is executed, the last one especially, it will not be run until all of them have been run. So this is what you mean by serial computing. So it runs in sequential. So when we talk about parallel computing, this is what it means. Okay, you can have an instruction running serially, but then you got multiple processors that is running at the same time. So at this clock T1, all these processors is busy running their own respective program. It can be a different program, it can be the same program, right? So that is what it means by parallel computing. Okay, that parallel computing is actually looking at a single system. That means the program is running maybe from the shared memory. But parallel computing can also be implemented or built using multiple computers. And each computer we call node. And they are interconnected by a network. Okay, if you interconnect them like this, they also can run in parallel as well. It doesn't mean that a single system is the only way to do parallel computing. No, you can actually do distributed parallel computing. So this is distributed parallel computing because we have different PC. They are running at the same time, and the data is shared through communication by sending messages between them through the network. Okay, so this is a more scalable type of parallel computing. Okay? Because one computer system, you have limitation. You cannot have too many cores inside there sharing the same memory. So you have to scale it out using this kind of distributed parallel computing. And most of our large supercomputer is based on this kind of architecture, right? In fact, Google, Amazon is using this architecture as well when they provide us the cloud services. So in here, you can see one computer can have multiple cores, and it itself run in parallel. Okay, and between these two also run in parallel. Imagine that you can have many more nodes that is connected through the network, and you can have much more parallelism in this case. But of course, your network bandwidth needs to be large. If let's say your network bandwidth is kind of small, then it will inhibit the performance gain as well, because the bottleneck is in the communication itself. So the network bandwidth needs to be large as well. But nowadays, we don't have to worry about it because you can see that the network speed is always increasing. In the past, we were talking about megabit per second. Now we talk about gigabit per second. I mean, the past also talk about gigabit, and then terabit per second. Now it's petabit, and we are going into exabit per second. Okay, giga is 10 power of 9. Peta is 10 power of 12. Okay, exa is 10 power of 15. That means you've got 15 zero at the back there. So exa is quite large. Of course, now we say that it's large, in the future might not be large. Maybe your grandchildren will be thinking, what? Exabyte? It's small. Okay, why use parallel computing? As we all know, you can save time or money because time, of course, definitely, if you run in parallel, if let's say you can parallelize the program, you can do the job at the same time. Like the field that you can see there, imagine that you have only one tractor is supposed to harvest the fruits or whatever, or wheat. It has to do alone. You're going to take a long time, right? But if you put many tractors there, of course you can save time. You might be able to save money as well. You might not be able to save money, but most of the time you can save money. If you're able to do at faster rate, perhaps you get more requests for your service. Okay? So you might be able to save money as well because you are doing a better job. Okay, what is more useful, especially for nowadays? We want to solve larger problem, more complex kind of problem. Okay, for example, we want to do simulation to find out, let's say for example, weather forecast. Okay, you have to simulate the weather so that you can predict whether there's any thunderstorm which is going to be catastrophic. Okay, and this can be very useful. Maybe for us it's not useful, but it's very useful for people who actually go to the sea. Okay, we have always heard that we got storm in the sea where the ship actually gets sunk because of that.
got many different kind of stories. But nowadays can be reduced. This kind of incident can be reduced. Why? Of course, we have sensors everywhere, to detect whether this can happen or not. But one of the important one is weather forecast. So you can weather forecast maybe 1 day ahead by looking at our measurement and also wind speed and all that. So we can forecast whether it will be of what kind of condition will happen and at which specific place, so that we can prevent accident from happening. Okay, or maybe looking at the weather forecast to find out whether tornado can happen or not. For example, of course here we don't have tornadoes, but in America you have tornadoes. So they have to find out whether tornadoes can appear and which direction that they go, right? So maybe the existing tornado, so they study get the data and then simulate for a couple of days to find out which direction that they will go. Okay, so it can save life, and it can also allow things to be safe step to be taken in advance. Some other larger problem like medication, let's say drug discovery and that, we can also use computing to do so. But nowadays, what are the most hot topics for computer science? Anybody knows? You should know, yeah. You use it every day.
AI.
Huh?
AI.
No, you say ChatGPT. You always use ChatGPT to find answers. Okay, there's nothing wrong to find answers from ChatGPT. Okay, and in fact, if you ask me, is it good to use ChatGPT to find answer? I think it's good, but don't find answer and just use it blindly. Because if you find answer and use it blindly, you're not learning anything. Why not? If ChatGPT give you the answer, you should go and question, okay, why it give you this answer? Or maybe, how does it do it? Then only you start to learn. And that's the correct way to do it. Okay? In fact, of course, a lot of university try to avoid, or maybe not avoid, but try to put some kind of restriction. The only thing that I think is you don't put any restriction, but you need to be aware how to use it in the correct way. That's the most important thing. Like for example, in my case, I also use ChatGPT as well. For example, if I'm lazy to go and Google and find out, because when you go Google, it never give you a clever information. But if I ask ChatGPT, they can scope it down, so I can go and search for that particular key point. Okay, the one that ChatGPT gives to me. ChatGPT is not always the best. For example, some of the questions I just want to try. I test ChatGPT. Some algorithms that is quite complex. ChatGPT able to give some answer, but the answer is incorrect. Okay, it's incorrect answer. It can give you some idea, but the answer is not correct. So you have to be a little bit careful about that and be aware of that as well. Okay, so ChatGPT sometimes is not always foolproof, giving you the correct answer. Because I asked ChatGPT, how do you find the answer? Do you learn, or do you go and search for the internet? Because always I see that it search the internet. It says two things. First thing is it has been trained to do that. Second, actually go and search from question and answer. Let's say Stack Overflow has question and answer, right? So you go and study it and then come up with its own solution. So it performs both. Okay, because I asked ChatGPT, I say, okay, this question, why it appears that you know, but you give me the wrong question, wrong answer. This part is wrong and that part is wrong. ChatGPT, if you tell them that this is wrong, this is right, or this is part is misleading, it can accept it, it can reply to you in a polite way. Okay, and then it can actually use your idea in order to come up with a better solution. So it shows that the ChatGPT is understanding what is happening and the idea of correcting its own mistake. Okay, that's one thing that I find quite interesting about ChatGPT. Okay, and ChatGPT of course uses parallel computing, right? And you see that it comes out slowly, right? It's not because Microsoft tried to limit or throttle the speed of giving you answer. No, is because that is the maximum speed that it can go. Okay, even though it's running on GPU, running on multiple cores, it cannot spew out so much information. You have to do one by one. That's why you see that the letter comes out. Okay, and also sometimes you see it comes out and then ChatGPT delayed it and then come up with a new one. Actually, it realized that it has done something wrong. Okay, you have to revert back and then redo again. Okay, so that is something that is very new that is happening where we use parallel computing, and that's why your GPU, if you want to buy it now, is very, very expensive because every big companies like Microsoft is buying GPUs for training their artificial intelligence. Okay, so now is not a good time to buy GPU, and in fact GPU is not the best processor to use for AI. There's a new idea right now. They try to come up with analog computer. Okay, currently every of the computer is digital. They found out that to solve AI in a faster and also with lower power consumption, they have to move into analog computer. In the future, we're going to learn analog computer, but not we don't know when. It'll be interesting. Okay, another thing about parallel computing is it provides parallelism. Here is it runs concurrently, but the correct word to use here is to provide concurrency. And of course, concurrency is very important. Just imagine that if you have to queue, like in a batch era, where if I want to write a program, I have to hand it over and I have to wait. Okay, because it run in a batch. One computer at one program running on a single computer at a time. It's not a viable solution. Nobody is going to wait. For example, you type Google search or you do ChatGPT. Do you need to wait for me to finish first? No. You don't have to wait for the next person to complete first. Okay, Microsoft is able to receive your command and start processing it. Okay, so that is parallelism already. So what we experience nowadays, we take things for granted, is actually happening in parallel. Okay, whether you realize it or not, that is the case for nowadays computers or the service that is provided by service provider like Microsoft, Google, Amazon, and so on and so forth. Okay, why use parallel computing? One thing is because you can take advantage of non-local resources. Okay, what are the non-local resources? So we have that. Only one slide. Okay, another thing is I think here is not that complete. I'm not sure whether it's supposed to be there. No? Okay, this slide actually comes from here. I put it out there. Okay, you can click on that. And it actually came from here. I discovered that it comes from this website. Okay, it has a letter right up there. You can actually read from there. Just in case that you miss what I say. Okay, you make better use of the underlying hardware. You can see this is one of the, I think it's IBM, can't remember what processor it's called. It has, here you can see we've got 6 cores. This is the core. The top here is the cache memory, level 3 cache. It's quite big as well. Okay, I think this one perhaps is megabytes of data. So this is the core. I think the core, inside the core has multiple processing units itself. PU. Okay, this is another one. This one I think is, I can't remember the name of this core. Is the project from 2 companies, if I'm not mistaken, IBM and Apple. We came up with this core. I cannot remember what it's called. Okay, and here it has 18 cores altogether. They call it processing unit. The last core is here, 17. And the rest are the I/O, input/output, to communicate with the chips outside. And this is the communication serialized and deserialized slot, okay, for fast communication. It's running at gigabit per second, or maybe nowadays terabit per second. So you can make full use of the multiple cores inside the processor nowadays. Everybody is moving horizontally, that means expanding or scaling horizontally rather than vertically. Horizontally means you don't increase the speed, but you increase the number of cores. Okay, if you scale vertically, you are increasing the performance. Basically means increasing the speed rather than creating multiple cores. Okay, the motivation for parallelism. We have a limitation of the hardware. I mentioned to you, sorry, this one. Limitation of the physical limitation of the hardware. So you have to go in parallel. And also, nowadays, it's easier to find parallel programming libraries. Okay? In the past, we don't have that. Nowadays, the library is easy to find. Not only libraries, you can also get help, a lot of help. A lot of books, a lot of people actually discuss this question and answer in the internet. If you bump into a problem, you can always go to that forum to ask your question. Okay, not only that, hardware is also available, bundling right now. The GPU is easy to find, and of course now is not a good time to buy. You have the hardware off the shelf. Okay, you don't have to go and create it. Okay, because you can buy it. Okay, the trend in microprocessor is also not only the GPU, the processor is also making some advancement. Of course, we are also thinking about increasing the speed as well, not always start at 4 gigahertz. If you can remove the heat management, handle the heat management, you're still able to increase the clock speed. Okay, nowadays, if you heard in the news, they try to move away from silicon because silicon, like I mentioned, you already hit the physical limit. Now they're going into graphite. Graphite is actually carbon. You know the carbon in your pencil is actually can be semiconductor. If you want to know, you can actually take your pencil, you draw, you just scratch on certain surface. Okay, and then you try to put electricity, you can see that you can actually conduct electricity. Not so good, but it can conduct electricity. And in fact, semiconductor means able to conduct and able to not conduct. That's why it's called semiconductor. Semiconductor. So you got insulator, which does not conduct electricity. You got conductor. In between is semiconductor. Okay, what is good about semiconductor is this. Because it can conduct and also cannot conduct, right? And the good thing is, you can switch between conduct and not conduct in split second. And that's why you got this computer, because you can switch on and off very quickly, right? And you can do it in split second, in gigabit per second. And if you do it on graphite, you can do it in terahertz. Okay, so if we able to come up with computer using graphite, we can break our clock speed limit from gigahertz to terahertz. Okay, terahertz is 1,000 times 1 gigahertz. Okay, if 1 terahertz, that means 1,000 gigahertz, right? And graphite also do not generate much heat. Okay, but of course we have problems, still problem. They are still trying to find out if they can manufacture. Okay, but right now in the lab, they're able to come up with graphite, small graphite logic gates. Okay, and they say that it can run at terahertz. Okay, so we got some kind of improvement in research for microprocessor. In the future, you can see a single processor that is running terahertz. But of course, at the same time, we also want to have multiple cores that run in parallel as well. Okay? So we can pack more transistor into the silicon die, and also execute them at faster speed. So what kind of level of parallelism that we can do? We can do at high level, we can also do at low level. So let's have a look at the level of parallelism. So we can have multiple processor, there is a processor level, that means parallelism at processor level. We can have multiple computer run in parallel, so that is a computer level of parallelism, which we call parallel computers. Okay, and we can also have not just the core that is parallel. So we got the computer core that is running in parallel. We have parallel computer, parallel core. We also have what is known as superscalar processor. The processor itself can do parallelism. Okay, one core can also do parallelism. Okay, in fact, we have instructions that is able to execute one instruction but multiple data. Okay, that's why the name comes in. You saw the name just now. Single instruction, multiple data. It's basically talking about here. So we've got three levels. The first one is a computer parallelism, the core parallelism. That means one processor with multiple cores, and the core itself has instruction that can perform many jobs at the same time. That means single instruction, multiple data. You can process multiple data using one single instruction. Okay, the next thing that we want to look at is how do we construct the computer. And we also have to look into the memory, because memory is one of the important component of the computer. You have the processor, but you don't have memory, is nothing as well. That means the computer is not functioning, right? So you need to have both. You need to have the CPU that is processing, and you need to have memory. If you want to have parallel computer, then you have to look into how you share this memory, right? Now, if you have equal amount of sharing, that is called uniform memory access. That means this architecture, when we design it, we put all this CPU in this system, and this memory is shared, and everybody has the equal share. We call it uniform memory access kind of architecture, right? Or UMA. But we can also have a different kind of architecture. Okay, so you got CPU here, number of cores or number of CPU sharing the memory. They might share in UMA, that means unified memory access, that means it's all equal. But between these two is not equal. Okay, so this core here and this core can share this memory equally. Okay, its own memory is shared equally. It can also access the memory here using this bus interconnect, using this communication channel. But right now it's not equal, because this bus interconnect here might be a bit slow. Okay, and the memory that is provided to this CPU is limited. So you can have a shared memory inside this cluster, but this memory in total is spread or distributed among the clusters. Okay, so this CPU can have a big advantage if they are using this memory. But if you try to use the memory here, then it has some disadvantage. Okay, in this case here we call it non-uniform because it's not uniform. Within itself is uniform, but when you try to access the memory elsewhere, it's not uniform anymore. Okay, you have to, for example, if I want to use the memory here, I have to communicate to this cluster to help me grab it from this memory and pass it along. Okay, so it's no more uniform. So you can view it like this. If you want to run this program or process the data the most efficient way, if the processor is running here, you better put your data here. You don't put here, or everywhere else, right? And you don't spread it out to many other memory. You like to put the memory where the CPU is able to grab or get the data as fast as possible. So this kind of memory architecture is simpler to design than just now, and is especially useful if, let's say, you want more CPU, because you cannot have too many CPUs sharing the same data. Everybody is trying to use the same data. Just imagine that one toilet, every 5,000 people is trying to use the same toilet. It's not efficient, right? But what you can have is maybe a cluster of group, and they share one toilet. Okay, but this guy can go and use this toilet, but then it's better to use his toilet first before he goes to the other toilet, just in case that here is fully occupied. Then you can go and find out which other toilet is accessible. So this non-uniform memory access is of this kind of architecture. Okay? Not all processors have equal rights to access the memory. Sorry, I shouldn't say right, I should say equal speed of access to the memory. Here it says equal memory access time. Okay. Now, in the past, we have this kind of architecture where before we have multiple CPU. We also have parallel computing at that time. So our CPU is only one CPU. It owns the whole memory. And in order to do parallel processing, you connect them to the internet. And this is also NUMA, okay? Where you have to send messages to every of the peers in order to get them to work together with you. Okay? And you can have a hybrid kind of architecture as well. Here is hybrid. You can see actually this one is UMA, this one is NUMA, and this is also NUMA, but the processor itself is different. For example, you have CPU and you can mix with GPU. Okay? So this is hybrid distributed shared memory. Okay? This one used in largest and fastest computer, especially a supercomputer, is using this kind of architecture. Okay, in the past, before thread was very popular, how do we run program? We run program by running the program individually, but you run them in parallel. Okay, so actually here we are not talking about parallelism. We are perhaps talking about concurrent programming models, right? So we can run the process, we can instantiate the process, 3 processes at the same time, and then it runs in concurrently, or maybe in parallel as well, because it might have multiple cores that process them. Okay? So this is the old way of doing things, but nowadays we have a different kind of way to run the program. Okay, it's thread model. So one process can have multiple threads inside there. Okay, so you can have threads that is running and doing the job in the process itself. Okay, not only you have process that can be can run the program in parallel or concurrently. You can have threads inside the process running concurrently or in parallel as well. Okay, so if you want to imagine, process is actually a heavy way of thread. Okay, thread is a lightweight. But if you run them concurrently, basically they give you the same effect. The only difference is how much memory or how heavy it is. Depends on whether you use process or you use the thread. Okay, process is heavyweight, so it's a bit slower. If you use thread model, it's faster. That's why thread actually comes out with a different kind of library. For example, 4.6 thread, the one that we use, the thread library. And then we also use OMP, right? So OMP is one of them. Microsoft Thread I never introduced to you, so we don't have that. We got Java, Python, many other languages also support threads as well. CUDA use GPU for parallel computing. So we got a lot of libraries that is helping us to make parallel programming more efficient and possible. Okay, if you use MPI, here it doesn't mention about MPI, I mentioned at the bottom there, MPI. If you use MPI, you can fully utilize the machine that is not, I mean, many more machines that is connected to the network, not only on the processor or multi-cores or multi-processor on a single machine. You can also take advantage of other machines, okay, provided that you are connected with one another, okay, and you can use this kind of model in order to solve your problem. Anyone here wanted to use MPI model in their assignment? Huh? Okay, but you have to use a number of computers. You have to start another computer. Okay, go and learn, because I haven't reached that part yet. Go and learn on how to actually instantiate the process on different machines. Okay, your program will not change. It's only how you actually design, plan your execution. Okay, you have to create a list, and then tell MPI exactly this is the my plan, and then this is the name of the host that, and the IP address that will participate in the processing, and then MPI will do it for you. Okay? You can ask ChatGPT how to do it. You want to. Okay, so ChatGPT can give you some ideas what kind of MPI command to issue in order to do that. Okay, there's another type of models, data parallel models. This one is used in some of big companies, not companies, sorry, bank. In banks, they use this. Okay, partition global address space, where they use all languages to actually access the data. So this global data, especially banks, you've got many branches in the country, not only locally, not only in the state, across country as well, right? So you have a massive data, so they use partition global address space in order to allow them to use and share safely the data. Okay, just now I was talking about instruction, single instruction, multiple data, right? That is at the processor level. Okay, the processor is executing the instruction, and that instruction can process multiple data at the same time using the same instruction. That is at the processor level, okay, or the core level. If you go up one level up, which is at the language level, programming language level, then we have similar idea but different name. Okay, we call it program rather than instruction. So you got multiple program. You can write multiple program. Okay, different file, and then you assign the core to run on this program. And you have done this many times in our exercise. Okay, for example, we do the CUDA. It's actually single program, multiple data. When we do OMP, it's also single program, multiple data. When you do MPI, we also do single program, multiple data. Okay? When we did some of our exercise using thread libraries, thread. Okay? Basically, we are doing this. Multiple program, multiple data, because each thread is running different program. Okay? If you remember P5, we did the thread, right? And we run different programs. Okay, one program is assigned to one task, one thread, and then the other program is running another thread. Okay? For example, if you remember, we did the apple juice and also throw out pair, remember? So you just imagine that this is clock pair, this one is introduced. Okay? Track 1 is assigned to this, track 2 is assigned to this. So there is multiple program. And it's actually using the same data, so it's single data. So the apple juice and clock pair program is actually multiple programs because they are using the same bag. The bag contains apples and contains pear, remember? So that is a simple example to demonstrate to you how this model is mapped into the actual program that you have done in the lab exercise. Okay, when you design the parallel programs, you have a lot of problems, especially when you deal with multiple cores, because you cannot use the original program that run on single instruction, or the old style, or I should say old style programming. We cannot adapt one-to-one. That means we take the original program and then just pass it into parallel computing system in order to let it run in parallel. You have to do something to it, okay? And that might not be easy, okay? But fortunately, we have ways to actually automate it. So we can do it manually. We also can automate it. The best thing is we can fully automate it. Okay, can we do that? Luckily, I think nowadays we can. In the future, if we use artificial intelligence, even better. Because fully automated means we can write a program which is running on single program, and then maybe we ask AI to go and analyze it, and then come out with the parallel computing code equivalent to that. Okay, so that will be fully automated. But at the moment, maybe it's hybrid in between automated and manual. For example, when we use Pragma OMP, right? So basically, we have control of using it manually or doing it in automatically. For example, we use a for reduction, basically is semi-automatic, right? Because the program, we don't have to adjust much. We just feed in the original program, and then we let the OMP do it for us. Okay, but we have to find out whether it can do it or not. For example, for reduction, of course it can do it. It can do it for you, but in general, it cannot do it for you. That one you have to wait until AI is capable of doing that for us. Okay, but at the moment, it's semi-automatic. Of course, we are targeting fully automated, where we feed in our ideas and then it will just analyze the ideas that we provide, or maybe the source code in using single program, and then it will adapt it for multiple processing or parallel processing. Now, most of the time when we want to automate it, we always focus on the part where it can give us the best performance. And most of the time, we always target the loops, because the loop is the one that takes a lot of time to process. Okay, that's why you can see for reduction is actually 4 in front, right? Because loop is very costly, and most of the time you can do parallelism on the for loop. Okay, that's why we use for loop. In fact, if you look at the GPU, also the same thing. Everything is repetitive. Okay, you repeat again and again, so you can parallelize that. And repetitive code is the one that run or use a lot of time of processing power. Okay, another one, if let's say it's not fully automated, we have to do it ourselves. Okay, we have to supply our own code in order to make it possible. Or maybe using a compiler directive, flags, in order to tell the compiler, okay, this part we do parallel, this part we do in single processing, and this part we do parallel. So you need to explicitly tell the compiler which part that you can parallelize and how to do it, and which part that you shouldn't do in serial and leave it as it is. Okay, in order to able to parallelize a program, you need to understand the program first, understand your problem first, and also your program, right? Some of the problem is easy. easy to parallelize. Most of the time is if it is not associated to one another. That means they are independent of one another. That one is easy problem. I'll show you some example later. What are the easy one? What are the difficult one? Some problem is not so easy. So you have to go and figure out how to do it. And some problem is even worse than that. You cannot parallelize at all. Like for example, in this case, you want to find the Fibonacci series. This you cannot parallelize it. You find it, you cannot do it. Why? Because in order to compute this number, the next number, you have to compute the previous one first in order to find the next one. Okay? For example, you want to find this 3 actually comes from 1 plus 2. So you get 3. This 5 here comes from 2 and 3. This 8 here comes from 3 and 5. But this 5 actually comes from 2 and 3, remember? So you actually rely on the previous data. So they are interdependent on one another. And this one is tightly dependent on one another. If you want to run each thread to compute their number, and each thread is relying on the previous thread to compute, and the previous thread also relies on the previous thread, basically there's no parallelism can be gained from there, right? Because everybody is relying on one another, so it has to be done in series as well. So it becomes sequential. Even though you can assign a parallel thread, but everybody has to wait for one another, so it becomes running in serial. Okay, so this problem, there's no way for you to do parallelism. So you have to look and understand at your problem. Can you parallelize or you cannot? Some easy, some intermediate, some is hard, and some you cannot do at all, like for example in this case here. Okay, so if let's say you can parallelize the program, what can you do? Most of the time we look at partitioning. There are 2 ways to partition. The first way is domain decomposition. Decomposition means how you break it. Decomposition means how you break it. First you break it on domain level. When you talk about domain level, you talk about the data. How you break the data. Data is the domain level. The second one, you decompose using functional decomposition. Okay? Functional decomposition is you decompose according to the code. So this you decompose according to domain, that is the data. This one is on the code. Okay, so there are 2 ways to partition. And how do you partition? This is how it looks like. Okay, let's look at the domain decomposition first. So you got one piece of data. Okay. In serial, maybe they have to handle all of them, but you have to look at the problem. Okay, can you break it down so that they can run in parallel? Okay, if they are dependent on one another, most probably you do not want to break them, right? But suppose this data set can be run independently from this data set. This one also can run independent from the rest of the data set, that means they are independent of one another. Maybe they are related to one another some part, but majority of the part is not independent, is independent. Then you can break down into such category. So make sure that this one is independent. And then you assign this processor to process each one of them in parallel. Okay? So that's what we do when we do domain decomposition. Okay? Let's say, for example, in our case here, we want to find the pi, because I use the example because it's easy and we've done it before, right? So find pi is basically you have 0 to 1, okay, and then you try to find the integral of this, and by breaking it down into smaller part, right? So basically what you're doing is domain decomposition. Okay, you're doing domain decomposition. You're breaking down the data into smaller chunks. Okay? And then why I can do that, why I can do domain decomposition, because in order to compute this area here, I don't rely on the next one. I can do it independently, right? The same thing when I compute this, do I rely on the next or the before one? No, it's independent. So that's the reason why I can break it down using this domain decomposition. So I can break it down like this. Now, when I break it down, the next thing I want to ask is, how do I execute. How do I assign the task to execute? Okay, let's look at this problem here and compare to what we have done. Remember, in our case here, we got how many tasks? Let's say we got 4 threads. But here we got more than the data itself. We can break it down into more than 4, right? So when I assign the task, because one thread can work on one specific data. So I assign maybe thread number 0, do this one. Thread number 1, do this one. And thread number 2, do this one. Thread number 3, do this one. So all together I got 4 already. Okay? And then I repeat again, starting from here, thread number 0, thread number 1, thread number 2, thread number 3. Okay? And then I repeat again, thread number 1, that's like 0, thread number 1, thread number 2, thread number 3. Okay? Because I got only limited number of threads, but I can decompose my data into independent piece of data. But because my processing power is less than what I have to repeat it. Okay? And that one is called cycling. The way I assign it is cycling. 0, 1 to 3, 0, 1 to 3, 0, 1 to 3, cycles. But I can also decompose in a different way, which I did not do, never do, which you can try if you're interested. And you try, and it should give you the same answer. You decompose by block. Instead of cyclic, we do it block. And how do we do it? Okay, let's look at the same problem. Okay, from 0 to 1 again. Right? I got 4 tracks. This one also 4. This one is cyclic. Now, how do we do it block? We do block like this. We got 4, right? And we know that we can break it down into smaller chunks. Yeah, we still have to break it down, but we categorize them into blocks. So this small area, we make it into blocks like this. Oops, sorry. We break it down like this. 1, 2, 3. So here is thread 0 is going to be assigned to this block. Thread 1 is going to be assigned to this block. Thread 2, thread 3. So this block is going to have many strips, a lot. So it's going to start from here to here. So it's going to do all. And here is going to start from here to here. This guy is going to start from here to here. So it's going to complete all of them, but in a block. So cyclic means we do 0, 1 to 3, 0, 1 to 3. Block means the whole thread, the whole block here is going to be executed by one thread. Okay, so when you decompose and how you assign to the task, you can do it cyclic, which we have done in the lab. But this one we never tried before. You can try it. Okay, and how do you write this code? It will be different, right? The way you write here and the way you write here is different. Okay, maybe you can try this. You see how different it is. But the result will be the same. Finally, when you get the result, it will be in the pi. This one also will be in the pi. Okay? So that is a 1D decomposition. Because our data is only 1D, one dimension. But if your data is 2 dimension, okay, you got x and y, maybe in matrix you got x and y, right? You also can partition it. For example, those who are doing image processing is 2D. Because why? You got x and y. Okay, and how you do you partition? You can partition using block. Okay, like this, it's a block. But because it's 2D, you can create a block like this in horizontal way. You cut it in horizontal way. So this block is done by thread 0, thread 1, thread 2, thread 3. If you're not happy, you can do this kind of blocking. Okay, thread 0, thread 1, thread 2, thread 3. Okay? Or you can do it this way. This one block, and this one block, this one block. It's okay. So it depends on how you're going to assign them. Either horizontally, vertically, or in boxes like that. Okay? Okay? But make sure that this one is independent of this. If let's say this one, if you do it this way and they are dependent, then you cannot use this time. Okay? If you find out that horizontally they are not dependent, but is dependent this way, but not dependent this way, then you choose this rather than that. Because the data, sometimes the data is, they are not dependent if it is horizontal, but if it is vertical, then it's dependent. Then you cannot assign it, you have to do it this way. Okay? So it depends on your limitations and also your liking. Let's say you don't have any limitation, then you can choose any one of them. But if you have limitation like I mentioned to you, then you have to choose the appropriate way. Okay? So this one is by block. But if you want to choose the way that we tried before, when we break it down, we can do it this way: 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. This one is cyclic, or cyclic in this way. This one is cyclic in horizontal way. This one is cyclic in vertical way. Okay? Or you can do cyclic in horizontal and vertical as well, just like what you see here. Okay? So 1, 2, 3, 1, 2, 3, 1, 2, 3, and then you repeat. Okay? So it depends on how you want to do cyclic, or cyclic, a single cyclic, which is horizontal or vertical. Okay, so that is decomposition, domain decomposition. You're looking at the data, and if the data are not dependent on one another, then you can decompose them in that way. But sometimes it's not so easy to, or maybe you are not doing parallelism on the data, but on the instruction itself, that means the code itself. So if that is the case, then you can do functional decomposition. That means the code is what do you call it? You categorize them in, you categorize the code rather than the data. And when you categorize the code, then you assign, let's say for example, this code is similar to one another or related to one another, and you assign tasks. Okay, what you don't want is this. This two is related, but you assign this part here to task 0, this one to task 1. You don't want to do that. Because you need to communicate between the two. Right? If they are related, that means there's some kind of communication that is happening. So you run in one task better. Because you don't need to communicate, you run in one task. Because the task itself is running there. There's no communication. But if let's say they are related, and you assign this task 0, task 1, then there will be some communication. So in that kind of case, you want to do functional decomposition, right? So in this case, this part here is related to this. So these two, it needs to be executed by a single thread or single task. This one is independent of one another. So this one is assigned to another task. And this one is another task, and this one is another task. Okay. Let's use an example. Just now I showed you example, right? This example here, I use this example. Another example is your image compression. Somebody here do image compression, right? Image compression you can do like this, you can do this because it's 2D. Most of the time I think image compression you prefer to do this. And the size here is 64 by 64. Is it right? Who's doing JPEG? JPEG is 64 by 64. So you can assign, if you use GPU, 64 core, 64 thread, 64 threads. Okay? And then this is one block, and then you can have multiple blocks in one dimension. Okay? And then you can assign this to the the SM cores of the GPU. Okay, GPU has a lot of cores, about close to 2,000 cores, so you can execute at the same time, right? So for image processing, this one is more suitable, domain decomposition. Now how about the functional decomposition? Functional decomposition, one example is those who are doing maybe say encryption. Okay, in encryption, most probably we want to do functional decomposition, or you can actually use both as well. But functional decomposition is possible in encryption and decryption. Why? Because the encryption, you got multiple steps to do. When you want to encrypt the data, first you have to do shuffling away. Okay? And then you have to do shuffling horizontally, shuffling vertically. Right? And then you want to use the what I call it? Cookbook in order to shuffle among here. So this one's cookbook shuffling. Okay? So it's the same data. This same data comes in. First you do normal shuffling, horizontal shuffling, vertical shuffling, and then cookbook shuffling, and then come out on the same data. Okay? So the data comes in. You do this process, you send this same data after the process to this next block to do the horizontal shuffling, vertical shuffling, cookbook shuffling, and then come out is the encrypted one. Okay? So you can see that you can do functional decomposition. Why? This task is going to execute this code that is going to do normal shuffling. And another task is going to do horizontal shuffling. And another task is going to do vertical shuffling. And the last one is going to do what I call it, cookbook shuffling. Right? And they can run this independently. Of course, you can say that you know, put the data in the cookbook shuffling, right? Isn't that this one, without this, has to wait? Yes, has to wait. And here, it also has to wait. This one also has to wait. Right? But what you can do is you can chop down your data. Okay? So your data can be chopped down into pieces. Right? So actually you're doing two things. You're doing function decomposition, you're also doing the data decomposition. But here I showed to you is the functional decomposition. So how do you do it? The pass in is in the here. Okay? So let's look at the time. Okay? You pass in here. So this one is empty, so it's actually wasted, not doing anything. Let's say this is 1, 2, 3, 4, 5. Okay. And when it is done, you pass this after you process it to the next one, right? So it's only do it here. And this one is all empty. But eventually, when it passes to the next one, it can take this one in. Okay? Right? And then when it passes to this, you have another track that is running, processing this. Now this one is passed to this, so it's running here. And you can take in the new one, which is here. Okay? So this is time. Right? So time is like that. So this is the first cycle, this is the second cycle, and the third cycle comes in, and this one passes to this, and this one passes to this, and this one passes to this, and you get a new one that's coming in. Yeah. Okay, now of course the first is not so good because this is resting, not doing anything, idle, idle, idle. This one, 2 is working, this one is idle, idle. This one, 3 is working, 1 is idle. But the last one you see here, everybody is working. Okay? And you can see that they run in parallel. Are they running in parallel? Yes, not the last one. There are 4 tracks, all of them are working at the same time. The code block shuffling is actually working on the previous, the very long time data. That's coming in during this period of time. It's only processed here. But at that time, this one is actually processing the data, the second data. Okay? And of course, later on you're going to pass this. But when you go down below, you can see that all of them are busy. So this is parallelism, but it's functional decomposition kind of parallelism. Okay? We got different code that is working on the data. Is that clear? So that is a functional decomposition example. Okay, so having said that, of course, the way I say this is though it's easy, right? Because luckily in our encryption, this data here does not depend on the data previously. all of them are independent of one another, and therefore you can do such thing. Yeah, no problem. Another example that is a very simple one is this example. Let's say your code, you're supposed to flip the color from black to white, white to black. Okay? So this square here, you want to flip it from, I'm not sure why it is blue, but right, you put one of color, let's say it's black, right? If it is black, you want to flip it to become white. This is white, you want to flip it to become black. This one is black, you want to flip it to become white. Okay? So what you can do is this. Let's say you got 4 tracks, then you assign this track 0 to handle all of them. Okay, and this track here is handle all of them. This track here, all of them, and this track here, all of them. Now, if you want to flip this color here, do you need to depend on the data next to it? No need, right? You don't have to wait, right? Because in color, you know, black become white, white become black, isn't it? So they are independent of one another, right? That means this track can actually execute without waiting for anybody, and all of them can run at the same time. So this is very easy. You don't need any communication between them, right? That means there's no need for waiting between them. So this is very easy one. Just like what I showed to you here, it's easy. But you have more difficult problem, which you have some kind of difficulties. For example, in this case here. Remember I mentioned to you that we do simulation, right? One of the simulation that we do is weather forecast. Weather forecast, you have something similar like this. Weather forecast is this kind of problem, where it is not easy to actually do parallelism. Okay? If you want to do parallelism, you have to look at how you actually break it down in the data. Okay? Let's say, for example, in this case here. If I want to simulate a problem where, a physical problem, where I put a heat here on this sheet of the metal, how does the heat is going to spread over time? I want to simulate this. I put a heat here on this metal. I want to study and simulate to find out how the heat radiates. Okay, the heat eventually will radiate out, right? So here is the hottest spot, will be this color. Here is a bit cooler, here is a bit cooler, and the blue one is the coldest of all, right? So as I apply heat over time, you can see that the heat actually radiates, right? I want to simulate this. How do I simulate it? I can assign track 0 to compute only this part here. Track 1, compute only this part. Track 2, this part, and track 3, this part. But you have problem, unlike this, you have problem here. Why? In order to compute at that point of time, what is the heat at that point of time, you have to look at the surrounding time. Because the heat radiates, isn't it? Yeah. So this heat here eventually will come from the heat from here. The same thing. The heat here will come from the surrounding. This heat here will come from the surrounding. Somehow, it has the dependency on some other data. You have to look at the neighbor data in order to compute its own temperature. Okay? So in this case, this task 0, especially when it deals with this part of pixel here, is to rely on the data before, the next track. So it means that this track needs to complete the computation before this track is able to extract the data to compute its own. Now you have some kind of dependency. Okay? So when you break it down, you have to find out, is it the best way to break it down like this? Okay? Or maybe you want to break it down like this, in a circle. That means this one track 1, and this one track 2, this one track 3. Okay? It is more complex, but you can break it down like that. Okay? The easier one is to break it down like this. Okay? But then the data needs to rely on one another. Unlike here, all the tracks don't have to communicate with one another because they can flip the color easily. Here, no. Track 0, in order to compute this, you have to ask track 1. Say, okay, here is at the border. I also need your data here. Can you give me this data? So he said, no, you cannot get the data here because I'm still computing. Why? Because I also need the data from here in order to compute it. So if they rely on one another before they're able to compute or calculate or simulate this. Okay, so that is a 2D heat diffusion problem, which is a physical problem that we face, especially when, for engineers, we have this problem. Okay, like for example, in electronics, also we have a problem similar like this, where we want to simulate how the electronics work at silicon level. So we want to see how the signal propagate from one another. So we can actually also apply parallel computing, but we have the same problem where the data is relying on one another. Okay, so the signal actually travel, propagate, so it has to rely on other threads to give the information, and this requires communication and is expensive. Okay. What I'm trying to say here is this: it's not impossible to do parallel computing in this kind of case, but there is some kind of dependency. Okay, so you have to design in a way such that that dependency is the least. Okay, it doesn't mean that you cannot do parallelism. That you can do, even though they rely on one another. Of course, when they rely on one another, the speed is reduced. Okay, you will not be as good as the problem above. This one will be slower than the problem above, but you're still able to do some kind of parallelism. For example, in this case here, if I want to compute the temperature here, because I only look at the surrounding temperature, which is close by. So probably this temperature, when I compute, I don't have to ask the information from there. So this one is independent. But this one, no. This one is dependent on the neighbor. Okay, this one maybe a little bit. And here is not at all. So there's certain part that you don't have to do much communication, but there are other parts that you need a lot of communication. Okay? Okay, so having said that, so there are a number of factors that you have to consider. We have talked about just now. So there are inter-task communication that is going on. We have to weigh that. Okay, finding out how to actually reduce this in order to make our parallel computing faster. First thing is, we need to reduce the communication overhead. Okay, if there's dependency, can we reduce it by maybe when we cut it, we don't cut it like this, we cut it in different manner. Maybe we cut it like this to reduce communication, or maybe cut it like this to reduce communication. Okay? Depending on the overhead. So you have to look into it. Okay? Second thing is, if you are doing distributed parallel computing, then you also need to look at whether you have the bandwidth, right? The network is enough to do that. If it is not enough, maybe you want to bring them closer. Let's say, for example, in this case here, this one is computed in US, this one is computed in Malaysia, okay, this one is Japan, right? Okay, so the one that is related to one another, you want to put in Japan. You don't want to distribute it in US and Malaysia. Okay, the one that is related to one another, you want to put it in the same place, so that if there's communication, it's within this Japan area. It does not need to go into US and extract the data, because it's a very long time to extract, right? So we have to look into how fast we can extract, whether we need bandwidth, right? Okay, so when we do the decomposition, where we put the data is where we put the data on the code is very important. Okay, the third one, visibility of the communication. The fourth one, whether the communication needs to be synchronous or asynchronous. Synchronous means you have to wait for one another. Asynchronous means you don't have to wait. Okay? Some you ask and then you have to wait. Some you ask while it is trying to give you, there's some delay there, you can still work on certain other things. Okay, so you're not wasting any time. So this one is bad, this one is good. Okay, asynchronous communication. That means you can work on something while you're waiting. This one, wait for the data to come. Okay, or wait for the process to complete before you're able to start. Alright? And then the scope of the communication. And the final one, the efficiency of the communication. How can you improve the efficiency? For example, do you send text or do you send binary? If you send text, then perhaps it's not so good. So change your communication. Instead of sending text, you send binary. Okay? Because in text, let's say in text you send 1, 2, 3, 4, 5, 6, 7, 8. In text, this is 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, 6 byte, 7 byte, 8 byte. Right? So 8 bytes to send this number. If you send in binary, perhaps this one is only, you can put into 4 bytes only. Integer. Integer is 4 bytes, isn't it? In binary. In text is 8 byte, but in binary it's only 4 byte, half of it. So you have to look at the efficiency of the communication, how you design the communication, right? And here is just showing you that how you communicate. You either broadcast, when you broadcast all the same data. Scatter, that means this is the data, but different process is going to run on different piece of data. So you scatter and process it, and later you have to gather. Okay, you gather it back. After you process and then you gather. So you got scatter, gather. Actually, we have some of you haven't tried. I think most of you haven't tried this exercise in P6. P6, you see some scatter, gather. We're going to talk about this in practicals. How you assign the data to different tasks, and then how do you collect it back? Okay, let's get together. Okay, when you're designing this Opel program, you also have to look at the granularity. So what is granularity? The granularity is there are two different types. The first one is fine granularity, and the other one is coarse granularity. So what is granularity first? The granularity is actually talking about this. It's talking about computation and communication. Okay, remember, right now I'm talking about not this kind of problem. If your problem is like this, then you are very lucky. Okay? Because your problem is like this, you're very lucky. There's no communication that is needed. Okay, but most of real world problem is of this kind, where is somewhat dependent on one another, and therefore you need to communicate. So here, what we are discussing here is actually that. Okay? So let's say we are talking about that kind of problem where the data is dependent on one another, and you cannot escape from having the tasks communicate with one another, right? Okay, so how do you deal with this kind of communication? You can communicate, which you cannot escape. Somehow you need to communicate because the data is dependent or the process is dependent. Okay, you communicate, you spend your time communicate, and then you also spend the time to process. Okay, you process, then you communicate, you process, then you communicate. So the granularity means how big is this? The ratio. Okay, the ratio of this communication over processing or computation. Here it's called computation. Yeah, I think it's best to use computation and process because otherwise you get mixed up with process. So here's computation. Okay, here I should say time. Communication time required, computation time required. So that is the ratio here is the granularity. Okay? That means how much time you spend communicating and how much time you compute. Right? Of course, when you compute the time, this communication is related to your computation. For example, just now when you compute the temperature, right? You have to ask the neighboring task the surrounding temperature. Okay, so before you're able to give that surrounding temperature, the task itself have to compute it. So it has to compute first before it disseminate the information. That is the communication. So how much time that it spent to compute, and how much time is spent to communicate that information to other threads is the granularity. How much time they spend here, how much time is spent here. So if this is small, if this ratio is small, it means that this is small, this one is big. Okay? Okay, small granularity, small, means communication is small, but the computation is big. Okay? If the granularity is coarse, this one is fine. If it is coarse, sorry, coarse, spelled as A-R-S-E, coarse, it means that the communication is high, the computation is small, comparatively. Okay? Right? So that is the meaning of fine grain parallelism, coarse grain parallelism. Do I have time? I don't have time. Okay, so this is how it looks like. How much you spend processing and reading, how much you spend to communicate that information. Okay? So this is fine, this is coarse. Okay, or this one, you can see that this is, I should say, this is fine, but this one is coarse because the computation is larger than the computation. Okay? So which one actually is better? The top one or the bottom one? Okay, the bottom one actually is better because you spend more time processing. You spend less time communicating the information to other tasks. This one is better. Okay, we want this one rather than this. But unfortunately, not always we can get this. Sometimes we cannot do this. We have to do this. Okay, we have to spend sometimes on computation. Okay, and then we have to communicate immediately. Okay, and the amount of processing is more or less the same. So this one becomes fine grain. Okay, if you are lucky, then you can spend a lot of time doing the processing, and then a little bit of time that is spent to communicate. That is send the information to other track that is needing or relying on this data. If you are lucky, then you get this, and this one is the one that we have done. But not always that we can get this kind of opportunity to solve our problem. Okay, so you have to look into this as well. What you can do, if let's say for example you can avoid this, can you design in such a way that you can avoid this so that you get this? Sometimes your problem looks like this, but you adjust a little bit, it becomes like this. Then it's better for you to adjust. Okay? Okay, I don't have enough time there, unfortunately. I have a few more slides to talk about it. And this one is related to QDAC. And this will come out in exam. So I know that it's going to come out in exam. So I tell you first. Something related to QDAC. And that's the reason why I want you to do the test yourself. You can go and ask ChatGPT and all that, but please understand what ChatGPT give you the answers. Don't just copy blindly, because if you copy blindly, you will never learn anything. And you're not able to answer the exact question also. Right? Use ChatGPT wisely, that's what I'm trying to say. Okay? I'm going to give you the code.
This one, the IO one.
No, not the IO. The QDAC. You've done some of the QDAC already. But I'm going to talk about it later, or more in the practical and also in lecture.
So from the beginning part where you talk about the history of parallel computing, all those things were not achieved.
That is theory. Okay? But in exact is more on the practical side. How do you write it? That means you have to know what you learn.
Maybe we can talk about this era.
Oh no, that one will come up. I'm just giving you some idea of the computer architecture in the past. So this one is simple. It's all 8843.
From the taxonomy of computer architecture onwards.
Yeah.
So we study from Flint's taxonomy onwards.
I will tell you where you have to stress. Okay? I will tell you where you have to stress. But definitely the exam question, the code, there is some coding. Yeah?
Sir, I think the stuff you write on the whiteboard is totally reversed from the slides.
Huh? Correct?
Say computation over communication. That's why.
I made mistake here, you are saying?
Yeah. The slide says opposite, and then your
Oh,
whiteboard comes.
okay, I think I made mistakes. Sorry about that. Is it I made mistakes? Check. Oh yeah, correct. Balik, yeah, I put the balik. So you have to adjust it. Sorry, I made mistakes.
I just passed the time for the attendance.
Yeah, come over here. I think we have to go now. We do it outside. Okay, those who miss, please come outside because the lecture is waiting.
Okay.
Okay, attendant eh?
No, balik. This one is communication.
What's the attendant one? So the attendant called. Forget.
Okay, you come forward. I'll because the lecturer is waiting. Can we go outside?